Hi, it's Julie, and this will be a quick video on the nerve impulse or action potential and how that works within the neuron. It starts off with a polarized neuron, and within the neuron there are sodium channels, potassium channels, and sodium-potassium pumps, which require ATP to transport 3 sodium out and 2 potassium in at a time to maintain a certain concentration gradient. And this makes sure that the inside of the neuron is always negative compared to the extracellular space. So this is when the neuron is polarized, and that's when there is no stimulus working on it to cause an action potential. Typically, neurons have a resting potential of negative 70 millivolts, and this is created mostly in part due to the active transport of the sodium-potassium pumps, making sure that 3 sodium are going out, which are positive ions, but that only 2 positive potassium ions are coming in, making sure that it's always more negative inside of the neuron. This purposely creates that concentration gradient, making it more negative on the inside. As well, this is also largely due to fewer sodium channels, which is seen in the photo, and negatively charged proteins and nucleic acids within the inside of the neuron, making it much more negative compared to the outside. So after achieving that polarized state that was just talked about, then if enough sodium gates open and the neuron charge passes a certain threshold value, which is negative 55 millivolts, then this causes even more sodium gates to open, so that a complete depolarization occurs and the charge goes up to positive 30 millivolts. This then causes sodium gates in neighboring parts of the neuron to depolarize as well. So this depolarization stage is when the sodium ions are flowing out of the neuron, making it a more positive neuron. This then causes even more sodium gates to open so that a complete depolarization occurs. This wave of depolarization along the neuron, making the neuron more positive, going up to positive 35 millivolts instead of negative 80 millivolts or negative 70 millivolts, which is the polarized or hyperpolarized state, is like a domino effect, so that shows positive feedback. This is causing a nerve impulse. So the nerve impulse travels down the length of the neuron as the sodium gates that are already open cause other sodium gates to open as well. These action potentials are all or none events, so that means that if the graded potential reaches the threshold, that means it'll go all the way up to positive 30 millivolts. But if the stimulus does not reach the threshold value, the action potential will not occur. There are no stronger action potentials or nerve impulses. A stronger impulse will activate more neurons, but each neuron's impulse is either all or none. To get back to the resting potential of negative 70 millivolts, the sodium-potassium pump continues to move 3 sodium out and 2 potassium in. Once the charge has reached positive 35 millivolts, then repolarization will occur. So the potassium gates will now open, allowing potassium from the inside to flow out, making the neuron's charge to become more negative as it was in the beginning. If enough potassium flows out to reestablish the original polarization, this is called repolarization. Usually the amount of potassium leaving actually causes the neuron to become more negative than it originally was in the polarized state. This is called hyperpolarization. So it goes down to a charge of negative 80 millivolts instead of negative 70, allowing the nerve impulse to travel in only one direction only. To reestablish the original distribution, sodium-potassium pumps, which use active transport using ATP, pump sodium back out and bring potassium inside. It takes time to do this, and this time is called the refractory period. So this is from the time that the charge reaches the threshold value to after hyperpolarization has occurred and the charge is back to the polarized state. During this time, the neuron cannot respond to another stimulus, so only one nerve impulse can happen at a time. So it's the amount of time it takes for a neuron to be repolarized back to its normal charge. So here's a quick overview of the action potential or nerve impulse. First of all, we start with the resting potential, so that's a polarized neuron that has a charge of negative 70 millivolts. and the sodium-potassium pump is constantly working to pump 3 sodium out and 2 potassium in to maintain that concentration gradient. Then a stimulus can occur, and if the stimulus is strong enough and opens up enough sodium gates, then this causes the threshold value potential of negative 55 millivolts. Then, if enough sodium gates open, this causes a full action potential. And so the sodium gates are open, the potassium gates are closed. This is depolarization. Once it reaches positive 35 millivolts, then the sodium gates close and the potassium gates open, causing repolarization. When more potassium flows out than necessary, this causes hyperpolarization and a charge of negative 80 millivolts. This ensures that the nerve impulse travels in only one direction. Because a nerve impulse can only occur where the charge of the neuron is negative 70 millivolts. So that's it for the nerve impulse or action potential, and I hope that was helpful.